Okay, this is lesson 4.5, and in this lesson, we're going to look at properties of exponential. The purpose of this first lesson will be to introduce two of the exponential parent functions, and then over the next lesson 4.6, we'll look at some transformations. So we can use the same general form for all transformations that we've been doing so far on the exponential function, where we define the function as f of x equals b to the exponent x. B being our base. So we can have two kinds of bases. We can have bases which show exponential growth and bases which show exponential decay. The bases that show exponential growth are when you have a base value of greater than 1. And that's because, as we know in exponents, the base is the number that's repeatedly multiplied. And if you're repeatedly multiplying by a number that's bigger than 1, you're going to grow. The number is going to get bigger. Decay is defined between 0 and 1 for the base, and that's because if you repeatedly multiply by a fraction like a half, the number will get smaller. As long as the number is less than 1 but bigger than 0, repeated multiplication will make a number smaller, and that's why we have decay. So growth when the base is bigger, decay when it's less. We'll look at some properties of both of these functions. There's one other scenario when the base is less than 0, and we don't have a definition for that function. And if you think about what a base that's less than 0 would look like, and then play around with some x and y values, you may see why it's undefined. We'll focus on exponential growth and decay. In terms of properties such as domain and range, I've gone ahead and graphed the two parent functions, 2 to the exponent x and 1/2 to the exponent x, so you can see a picture of their graph. And as you can see, 2 to the exponent x for very small negative values, large negative values, sorry, we have a very small y value. And as we approach 0, they get slowly bigger until we get to 0, and 2 to the exponent 0 would be 1, so we have a y-intercept of 1. I'm going to add that to my properties list, y-intercept of 1. And then after 1, since we're repeatedly multiplying by 2, the number gets bigger quicker, and that number grows quite rapidly. Now, the bigger the base, the more quickly it grows. If b is greater than 1, the greater the value of b, the faster it grows. Now for decay, I'm going to add my arrows here, we kind of have the opposite. The negative values would flip the base, so it would become 2 over 1 for negative values, negative exponents, and that's why we have large y values to the left of the y-axis. And as we decay, because we're multiplying by a half, the number is getting smaller to 1, and then continuing to decay almost to 0, but never getting to 0, only approaching 0. And as we've seen, when graphs approach lines, but don't cross them, in this case, we're likely dealing with an asymptote. And both exponential functions, growth and decay, have a horizontal asymptote. And without transformations, just for the parent function, it's y equals 0. Transformations can shift that asymptote, as we'll see in the 4.6 lesson. So in terms of describing the graphs further, we can describe the exponential growth graph as an ever-increasing graph. As x increases, f of x also increases. You could also read right to left and get a similar result. It would be decrease, decrease. For a decreasing interval, as x increases, so as we go left to right, what's happening to our graph? Well, it's decreasing. Increases, decreases. In terms of domain or range, whether it's the growth graph or the decay graph, the domain is simply that x belongs to real. Any real number can be plugged into the exponent to get a y value. And for the range, all of these values don't cross the asymptote here at 0, so we have y is greater than 0. So y belongs to real, such that y is greater than 0. Not equal to, because we're not touching the x-axis. All right, so there's our properties of our two base functions, and as I said, in 4.6, we'll do some transformations of those graphs. The second purpose of this lesson is to show how we can look at a table of values and determine whether a function is exponential. In previous math courses, you may have looked at tables and done something called first and second difference. And by doing the first and second difference, you can decide whether a function is linear or quadratic. And it kind of teases the answer over here. But if we look at a first difference, what we're doing is we're examining if the graph is linear. If we look at a second difference, we're likely looking to see if the graph is quadratic. And how we can tell is if the first differences are constant, the graph's linear. If the second differences are constant, the graph's quadratic. If the first differences were constant and it's linear, we don't need to continue to do quadratic and the next one we're going to introduce. We would just stop because it's a linear function. We don't need to consider any other options. But if they're not constant first differences, then we can look for second differences, see if they're constant. And if neither of those are constant, we can look at something called the Y ratio. And the Y ratio will tell us if it's exponential. Exponential. And the question every time is it constant? And if it's constant, that means it's either linear, quadratic, or exponential. So let's look at our table. We'll do first difference, second differences, and ratio, and we'll see if we have a linear, quadratic, or exponential relationship. So first difference just means we're comparing the Y values, and we're looking to see if the numbers are going up or down, and if they're going up or down, by how much. And we can do that by doing some subtraction. The second subtract the first, so 16 minus 32. That's down 16. Another way is by inspection, just looking at the numbers. 16 to 8 would be down 8. You don't need to do the subtraction if you don't need to. Next one would be down 4, down 1. Sorry, that number in the table is wrong, I just realized. Sorry, down 2 and down 1. Please make that correction to your table. Second differences, what we do is we compare the first differences. So from negative 16 to negative 8, that number is getting bigger. It's actually going up by 8. And we could confirm that by doing the subtraction. The subtraction would be negative 8 subtract negative 16. And if we do that, we get positive 8. The next one's positive 4, then positive 2, then positive 1. So the first differences are not constant. Those are not the same number, so it's not linear. The second differences are not constant, so that's not linear. The last thing we can do is look at the Y ratio. You can do Y ratio of second differences. I like to just do the Y ratio of the Y values. So going all the way back and comparing these, that's why these were grayed out. I'm going to use these spots. Let's do some Y ratios. The first one is 16 and 32. Ratio means divide. We would divide 16 and 32 instead of subtract. Here we subtracted 16 and 32. To do a ratio, you divide. So dividing 16 and 32 gives us a half. The next pair is 8 and 16. If we divide 8 and 16, a half. If we divide 4 and 8, 1/2. If we divide 2 and 4, we get 1/2. If we divide 1 and 2, we get 1/2. And now, for the first time, we see something that's constant. We have a constant ratio. So, since we have a constant Y ratio, what that means is we have an exponential relationship. So, given a table, we can look at first difference to find if it's linear. Second difference is to find if it's quadratic. And if it's neither of those, we can do a Y ratio of the ratio of the Y values, the Y ratio, and see if it's exponential. And in this case, it was exponential. And in fact, this half has significance that we'll see going forward in the unit. So purpose of the lesson, twofold. Can you look at a table and decide whether it's linear, quadratic, or exponential? And can you have an understanding of the properties and graphs of two of the exponential base functions? So in this case, 2 to the exponent x and 1/2 to the exponent x, and their properties: domain, range, y-intercept, and asymptotes. Okay, that's it for lesson 4.5. I will see you next time for lesson 4.6.